Hello, friends. Good morning.
Good
Good
morning,
morning,
sir.
sir.
Let us pray. Okay. We have finished the yes block elements. We have finished. Now let us go to the P block elements. The P block elements. Still some are coming here. Okay. Let us continue with the P block elements. Now we can define what are P block elements. Do you remember the S block elements? In the S block elements, when we write the electronic configuration, the last electron enters S level. So, in the P block elements, while we write the electronic configuration, the last electron enters a P level, enters P level in the outermost shell. While we write the electronic configurations of the P block elements, the last electron enters the P level. And these are the elements of a group 13 to group 18. These are the elements of a group 13 to group 18. Group 13, 14, 15, 16, 17 and 18. There are 6 groups corresponding to P1, P2, P3, P4, P5 and P6. We know the maximum capacity of the P level, that is equal to 6 electrons. 6 electrons. So corresponding to the maximum capacity 6 electrons, there are 6 groups belonging to the P block. Say P1, P2, P3, P4, P5 and P6. So there are 6 groups starting from group 13 ending with group 18. Let us see the general electronic configuration of these elements, the P block elements. The general electronic configuration, outermost shell configuration, the valence shell electronic configuration of P block elements will be Ns2, N P1 to 6. NS2 N P1 to 6. The NS level completely filled up. The NS level is completely filled up. There are 2 electrons. That is common for all the elements belonging to the P block. And the variation is in the number of electrons in the NP level. NP1, NP2, NP3, NP4, NP5 and NP6. So, the outermost electronic configuration, that means the valence shell electronic configuration of the P block elements will be NS2 NP1 to 6. NP1 to 6. So, the difference is in the number of electrons present in the NP level. The electrons difference will be in the P level, NP level. NP1 to NP6. See, all these electrons can take part in the bond formation. So, the oxidation number will be the same as maximum oxidation number of these elements will be the same as the number of electrons present in the outermost shell. That is S2 P1 to 6. All these electrons can take part in chemical bonding. And corresponding to that, there will be variable oxidation states also. But there are certain cases in which the S2 electrons are not involved in the bond formation. In some cases, the S2 electrons are not involved in the bond formation. And so, the oxidation state is corresponding to the number of electrons present in the P level only. Only the P electrons are involved in the chemical bond formation. The S2 electrons are reluctant to take part in the reaction, and that property is called the inert pair effect. That is called the inert pair effect. That means the laziness of the S electrons, S2 electrons, to take part in chemical reaction. That's called the inert pair effect. Pair means 2 electrons. S2, there are 2 electrons, a pair of electrons, and they are inert. They are not taking part in the reaction. And that is called the inert pair effect. So, due to the inert pair effect of S2 electrons, in some elements, the oxidation state is corresponding to the number of electrons present in the P level only. Normally, we can expect oxidation state corresponding to the total number of electrons in the NS level and the NP level. That is the maximum oxidation state possible. The maximum oxidation state possible is the sum of electrons present in the NS level and the NP level. That will be the maximum oxidation state possible. But in some cases, the NS electrons, S2 electrons, are not taking part in the reaction. So, the reaction is due to the involvement of electrons present in the NP level only. So, the oxidation number will be corresponding to the number of electrons present in the NP level. And the laziness, the inertness, the laziness of the NS electron pair, NS2 electrons, to take part in the reaction, that's called the inert pair effect. So, due to the inert pair effect, some elements belonging to the P block, they show oxidation state corresponding to the number of electrons present in the p level, np level only. Then, if you examine the elements in the p block, these are the 6 groups at the right end of the table, periodic table. You know, at the left end of the periodic table, there are 2 groups, group 1 and group 2. They are S block elements. Right end of the periodic table, 6 groups, P1, P2, P3, P4, P5 and P6. That is group 13 to group 18. That is the right end of the periodic table. And these are the P block elements. Between the S block and the P block, there will be 10 groups. Say starting from group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And in these elements, the last electron enters D level. While you write the electronic configurations of the elements present in group 3 to group 12, that we study next year, the last electron enters the D level. And these 10 groups will constitute the D block elements. Okay. Now you examine the P block elements, group 13 to group 18. The 6 groups at the right end of the periodic table, modern periodic table. Can see that all the non-metals and metalloids, the non-metals and metalloids are seen in the P block. The non-metals, all the except hydrogen. All the non-metals and metalloids. What are metalloids? The elements which show the properties of both metals and non-metals. The elements which show the properties of metals and non-metals. They are called metalloids or semi-metals. They show the properties of both metals and non-metals. Okay. See, the non-metals and metalloids are seen in the P block. It does not mean that the P block consists of only non-metals and metalloids. That is not the meaning. No, in the P block also there will be metals. In the P block also there will be metals. We can see that. There will be metals. But the non-metals and metalloids, these are seen in the P block. That is the meaning. There will be metals also in the P block. But the non-metals and the metalloids, they are seen only in the P block. There is an exception, and that is our hydrogen. Now, you consider the bond between the non-metals. Bonding between non-metals. The bonding between non-metals, that is covalent in nature. There is a covalent bond between say non-metals. The bonds formed between non-metals, they are found to be covalent bonds. We have seen ionic bond or electrovalent bond. In that case, there is complete transfer of electron from one atom to the other. Ionic bond formation. And there will be sharing of electron pairs, that is covalent bond. Here, the bonding between non-metals is found to be covalent in nature. That is because the difference in the electronegativity values is very small. The difference in the electronegativity values, difference in the electronegativity values of the known metals will be very small. So due to small difference in the electronegativities, small difference in the electronegativities of the non-metals, the bonding between non-metals is found to be covalent in nature. You come to the oxides. We have studied that non-metal oxides are acidic. That we have studied in the 10th standard. But it is not sure that all the non-metal oxides are acidic. There may be neutral oxides also. So we can say the non-metal oxides are acidic or neutral. For example, you take the oxides of nitrogen. Nitrogen is a non-metal. Oxides of nitrogen. Say nitrogen gives a number of oxides. There is a nitric oxide NO. There is a, say, nitrous oxide N2O. Nitrous oxide N2O. There is a nitrogen dioxide NO2. There is a nitrogen trioxide N2O3. There is a nitrogen pentoxide N2O5. Say a number of oxides are formed by nitrogen. Nitrogen is a known metal. And if you examine the property of these oxides, you can see that, say, nitric oxide NO and a nitrous oxide N2O, these are neutral oxides, neither acidic nor basic. While NO2, N2O3, N2O5, all these are acidic oxides. So we can say that the oxides of known metals are acidic or neutral. But you take the oxides of metals. We have studied in the 10th standard. Oxides of metals are basic in nature. They are basic in nature. There are a few metals like zinc, aluminum, etc. And their oxides are amphoteric. That means the oxides show the properties of acids as well as bases. They show the properties of both acids as well as bases. And they are amphoteric. But majority of the metal oxides are basic in nature. Sodium oxide, say Na2O, potassium oxide K2O, magnesium oxide MgO, calcium oxide CaO, say all these oxides are basic in nature. While aluminum oxide Al2O3, zinc oxide ZnO, they are amphoteric. They can react with both acids as well as bases. These oxides can react with the acids as well as bases. And so, they are amphoteric in nature. Anyhow, say vast majority of the metallic oxides are basic in nature, while the oxides of known metals are mainly acidic. There will be neutral oxides also. Okay, so that is about the general description of the p block elements. Let us see the p block again. In the p block elements, the last electron enters a p level in the outermost shell. The last electron enters a p level in the outermost shell, in the valence shell. And these are the elements of group 13 to group 18. There are 6 groups: 13, 14, 15, 16, 17 and 18, corresponding to P1, P2, P3, P4, P5 and P6. So we can write the general outermost electronic configuration as Ns to Np1 to 6. Np1 to 6. The general electronic configuration of the p block elements. The oxidation state is corresponding to the number of electrons present in the valence shell. The number of electrons present in the outermost shell. That means the total number of electrons present in the S level and the P level of the outermost shell. There are electrons in the S level as well as P level. So the total number of electrons will be corresponding to the maximum oxidation state. But in some cases, in some elements, especially in some metals, the S electrons, S2 electrons, NS2, S2 electrons are not involved in the bond formation. And that property is called the inert pair effect. Inert pair effect. Due to inert pair effect of the S2 electrons, the oxidation state will be corresponding to the electrons present in the P level only. P level only. Now, if we examine the properties of the elements present in the P block, we can see that all the non-metals and metalloids are seen in the P block. The non-metals and metalloids are seen in the P block. Then, the bonding, you examine the bonding, the nature of bonding between the non-metals. The bonding between the non-metals is found to be covalent. The bonds are covalent bonds. That is because of a small difference in the electronegativities of the combining atoms, the non-metal atoms. The non-metal atoms will be having their own electronegativity values, but the difference in the electronegativity values of the combining atoms will be very small. So there is no complete transfer of electron from one atom to the other. So the transfer of electron from one atom to the other, that is blocked. There is no chance for the complete transfer. If there is no complete transfer, there is no chance for the formation of ions. No ions are formed. And if ions are not formed, there is no ionic bond. There is no ionic bond. So here we have only the covalent bonds. Come to the oxides in general. We have to study these in detail in separate groups. But as a general description, we can think of the oxides of the P block elements. Here, the non-metal oxides are found to be acidic or neutral. We have taken the oxides of nitrogen as examples. They may be acidic or neutral also. Then, the metallic oxides, they are mainly basic in nature. Basic in nature. But there are metals like zinc and aluminum whose oxides are amphoteric. Amphoteric means that the oxides can react with both acids as well as bases. Acids as well as bases. And that is called the amphoteric nature. So that is about the general description of the P block elements. Now, we have seen that there are 6 groups corresponding to P1, P2, P3, P4, P5 and P6. There are 6 groups. 13 to group 13, group 13 to group 18. You know, there are 6 groups. And out of this, we have to study only 2 groups belonging to the P block. We have to see only 2 groups. And the 2 groups are group 13 and group 14. Group 13 and 14, we have seen group 13, 14, 15, 16, 17 and 18. So this year we have only group 13 and group 14. So let us see group 13 elements. Say In the group 13, the first element is boron. Boron. And so, these elements are called boron family. Boron family. Usually, the groups are named after the first member of the group. These are, named after the first member of the group. So, first member is boron. Group 13, first member is boron. And so, the group 13 is called boron family. Let us see the elements. The elements in group 13. Point number 1. The elements in group 13. Which are the elements in group 13? I had sent you the notes. You know, the elements are boron, aluminum, gallium, indium, and thallium. Say boron, aluminum, gallium, indium, and thallium, thallium. These are the elements present in group 13 or the boron family. Say boron, aluminum, gallium, indium, and thallium. You know the structure of the group. Say the structure of the group is like this. Structure of the group. Say group 13. There is boron. Then below that there is aluminum. Then there is gallium. Then indium and thallium. That is the nature. From top to bottom, boron to thallium, boron, aluminum, gallium, indium, and thallium. Okay, now let us see the outermost electronic configuration. Outermost electronic configuration. So to write the outermost electronic configuration, electronic configuration, we can do one thing. We can take boron as an example. Boron, atomic number is equal to 5. So, the electronic configuration will be, as you know, there will be 5 electrons. So, 1s2, 2s2, come on. You complete? Achu?
2p1.
2p1. 2s2, 2p1. Similarly, you take aluminum also, that is a simple one. Aluminum, atomic number 13. So the configuration will be 1s2, 2s2, 2p6. So 6 plus 2 plus 2, 10. And there are 3 more electrons. 1s, 2s, 2p. Then 3s, 3p. The O-Bow principle. So 3s2, 3p1. Say the outermost configuration. Boron, 2s2, 2p1. Aluminum, 3s2, 3p1. Gallium, 4s2, 4p1. Indium, 5s2, 5p1. Thallium, 6s2, 6p1. So the general outermost configuration will be ns2, np. Come on. ns2, np. Evelyn, complete it. Come on, you look at the electronic configuration and you complete the general configuration.
1.
Yes, NP1. NS2, NP1. Yes, NS2, NP1. That is the configuration. NS2, NP1. That is the general outermost electronic configuration. Do you remember we had seen at the beginning the general configuration of P block. NS2, N, P1 to 6, P1, P2, P3, P4, P5 and P6. Here it is P1. So the outermost electronic configuration of group 13, that is boron family, NS2 NP1. Okay. If it is so, what will be the oxidation state, maximum oxidation state shown by group 13. Group 13. Normally, what is the maximum oxidation state? We know the oxidation state is equal to the total number of electrons present in the outermost level. Total number of electrons in the outermost level, S level and P level, total number is equal to 3. Total number of electrons, that is equal to 3. And therefore, the oxidation state, that is equal to plus 3. But in some cases, the S2 electrons are not taking part in the reaction. The S2 electrons are not taking part in the reaction. That's called the inert pair effect. And that is seen down the group. Down the group it is seen. So, down the group, the S2 electrons are not involved in the bond formation. So, what will be the oxidation state? Only the P electrons are involved. In the P level, there is only one electron, and corresponding to that, there will be plus 1 oxidation state. So, there can be plus 3 and plus 1 oxidation state. The plus 1 oxidation state is shown in the elements, especially the last elements, gallium, indium, thallium, etc. There will be the oxidation state plus 1. The predominant oxidation state is plus 1. That is because of the inert pair effect. Inert pair effect of S2 electrons. Inert pair effect. So due to that, there will be the plus 1 oxidation state. The S2 electrons are not involved in the bond formation. Okay. As a point number 3, let us consider the occurrence of some of these elements. Say, for example, elements of elements like let us take elements boron and aluminium. Only 2 elements are taken. Occurrence. Only 2 elements, boron and aluminium, are taken. That is point number 3. Occurrence means how do these elements occur in nature? How do these elements occur in the crust of the earth? How are they seen? They are reactive elements, and they are not seen in the uncombined form. They are seen only in the combined state, occurrence. Let us see the occurrence. Occurrence means the ores, the important ores of the elements. For example, you take boron. The important ores of boron are, you take boron, the important ores are, one is orthoboric acid. Boric acid. Usually it is known as boric acid itself. Boric acid means orthoboric acid. And the formula is H3BO3. H3BO3. That is orthoboric acid. One of the important compounds of boron. Another one, it's a very important one, that is borax. Borax is Na2B4O710H2. Na2B4O710H2. It is the tetraborate of sodium. Tetra means four tetraborate of sodium. It is borax. Borax is a very important compound because it has got a vast application, industrial application. You know, borax is used by the goldsmith, say ponkaram used by Tata and the goldsmith. Say when gold is purified, then borax is used as a flux. Say the goldsmith Tatan is using borax, ponkaram for cleaning gold. That is the application level in the metallurgy. Borax is used in medicines also. It has antifungal and say anti-inflammatory action also. It is used in medicine also. So all these are important compounds. So remember only two important compounds: boron, orthoboric acid, H3BO3, and borax, Na2B4O7, 10H2O. Let us think of the ores of aluminium. Aluminium is also a reactive metal, and so it is not seen in the elemental form. Aluminium is seen only in the combined form as its compound. The most important ore of aluminium is bauxite. Regarding the molecular formula of bauxite, say Al2O3 XH2O is generally given. Al2O3 XH2O. X is a variable number of water molecules. As an average value, it is seen as Al2O3 2H2O. Say very commonly it is given as Al2O3 2H2O. But as a general formula, bauxite is written as Al2O3 XH2O or NH2O. That is variable number of water of hydration, Al2O3. As an average, it's a very common compound oxide. It is Al2O3 2H2O. If Al2O3 XH2O is there as a choice for bauxite, you should give that answer. Say multiple choice MCQ is given. What's the formula of bauxite? If Al2O3 XH2O is given as a choice, you must give that answer. If only Al2O3 2H2O is given, then you give that answer. Okay? You give the Al2O3 2H. It's a common, the average common formula is Al2O3 2H2O. But in general, Al2O3 XH2O. And there is one more important ore of aluminium, and it is cryolite. Cryolite. It is Na3AlF6. Na3AlF6. Say a double fluoride of sodium and aluminium. Na3AlF6 cryolite. Let us think of the abundance of aluminium. The abundance of aluminium. See, in the crust of earth, aluminium is the most abundant metal. Aluminium, that is the most abundant metal. Aluminium is most abundant metal. See, metal. It is given metal. The most abundant metal, that is aluminium. Not as free aluminium, but as its compounds like aluminates or bauxite, cryolite, etc. You think of clay. Clay is aluminosilicate. Clay. In the world, wherever you go, there is clay. There is soil. In the soil, there will be aluminosilicate. So aluminium is there in the combined form. So, aluminum is the most abundant metal. Remember, metal, I'm not saying the most abundant element. Not the most abundant element. The most abundant element in the crust of the earth is oxygen. The most abundant most abundant element is say the difference. The most abundant element that is oxygen. Next comes silicon. Next comes aluminium. All these are in the combined form. So remember, all these are in the combined form. Please don't forget it. They are in the combined form. So the most abundant element, it is oxygen. Not as free oxygen gas in air. Not that. Oxide, then carbonate, sulfate, sulfite, say, or silicate, all these contain oxygen. Silica contains oxygen. Similarly, silicon, not a free silicon, as a silicate and silica. Silicate and silica in the combined form. Soil, I told, it is aluminosilicate. So aluminum is there, silicon is there, oxygen is there. In aluminosilicate, there is aluminum, silicon and oxygen. So the most abundant element is oxygen. Remember, in the combined form, not as a free oxygen gas as it is seen in air, not that, the combined form. So most abundant element oxygen, second comes the silicon, and the third most abundant element is aluminum. Third most abundant element is aluminum. But the most abundant metal, that is aluminum. Say, oxygen is a non-metal. Silicon is also a non-metal or a metalloid. Silicon. But aluminum is a metal. So the most abundant metal, aluminum. The most abundant element, oxygen. The third most abundant element is aluminum. Second comes the silicon. Third one is aluminum. So among the metals, not the whole elements, among the metals, aluminum is the most abundant element. Okay. So that's about the occurrence of boron and aluminum. It is your turn, no? Is it time to stop? Okay. So it is time to stop. We can continue in the next class. Okay, friends, I had sent you